So today's question here says, a smooth sphere of radius r is made to translate in a straight line with a constant acceleration a. A particle kept on the top of the sphere is released from there at zero velocity with respect to the sphere. Find the speed of the particle with respect to the sphere as a function of the angle theta it slides. Everything is given with respect to the sphere and we are supposed to find out the speed of this ball also with respect to the sphere itself. So, do you all understand? It makes sense if we work in the frame of the sphere itself. First thing is that. So, in the frame of the sphere, if we see the system, what will happen? As the sphere undergoes an acceleration towards right, do you understand that this particle which is kept on the top will experience a pseudo force towards left? M into A, if M is the mass of the particle, then this is the pseudo force that it will experience, isn't it, when it is kept on the sphere which is accelerating towards right. There are other forces also. There is a force of gravity mg acting on the particle as well as the normal reaction acting on it from the sphere. But understand that it is this force ma which effectively will push the particle backwards, and as a result of that, after some time we will find the particle to have reached over here, right, such that if it makes, let us say, an angle theta with the vertical and it has gained a speed v, let us say, in the process, then can we use the work energy theorem on this particle to find out its change in kinetic energy and hence the speed, right? Because we know the force is acting, we can find out the work that these forces will do by the particle, by the time the particle reaches at its new position making an angle theta. We can use the work energy theorem, find out the work done by all the forces including the pseudo force. I hope you all remember when we use the work energy theorem, it incorporates all the work done by all the forces, which includes the pseudo force, the internal forces, everything, right. So, when this particle reaches here, let us say making an angle theta, first thing is we can find out a few quantities over here which will be required. Let us say in the process of the particle reaching down over here, its horizontal displacement is x towards left, whereas its vertical displacement downwards is h. We will require both these values because we are supposed to find out the work done by gravity as well as the pseudo force. See that the work done by normal reaction at any point in time will be 0 because the normal reaction at any point will be perpendicular to the direction of motion. Normal reaction n acts perpendicular to the velocity, so no work done by normal reaction, right. So, when we work in the frame of the sphere and we use the work energy theorem here, work energy theorem says that the work done by all forces, which includes work done by gravity plus the work done by the pseudo force ma plus the work done by normal reaction should be equal to the change in the kinetic energy of the particle. This is the theorem, right, out of which we now know that the work done by normal reaction is 0 because normal reaction at any point is perpendicular to the direction of displacement. So, what will be the work done by gravity here? When the particle reaches from the position A to the position B, see that it undergoes a vertically downward displacement of h, which we can find out in a while. So, can we say the work done by gravity will be mg into h, the force of gravity, into the displacement in the direction of force of gravity, which is mgh, right, plus the work done by pseudo force on the same lines will be the pseudo force itself into the displacement in the direction of pseudo force. Now, the pseudo force is acting leftward. So, what is the effective leftward displacement? We have assumed it to be x. We shall find out its value soon. So, ma into x plus the work done by normal reaction is 0 and that should be equal to the change in kinetic energy, that is the final kinetic energy half mv squared minus the initial kinetic energy 0. The particle started off from rest. Now, the next thing is to find out the value of h and x in terms of r, the radius of the sphere, and theta. So, see carefully in the above figure, see that this length is r, the length OB is r, the radius of the sphere, and in terms of r and the angle theta over here, we can easily write x as r sin theta. using trigonometry, right? This particular length here will be r sin theta. On the same lines, do you see that h can be written as this total length which is r minus this length which is r cos theta. So, it will be r minus r cos theta, which can also be written as r into 1 minus cos theta, right. So, now we can substitute these values above. So, this implies mg into r into 1 minus cos theta plus ma into r sin theta is equal to half mv squared. This is the final equation that we are getting. See that m cancels out throughout the equation, and we can take the 2 on the other side to get 2 gr into 1 minus cos theta plus ar into sin theta 2 times that is equal to v squared, and hence the final velocity v would be nothing but square root of, if we want we can take 2r common out of the whole thing, and inside we will be left with g into 1 minus cos theta plus a into sin theta, which will be the final answer for the speed of the particle.